Let's take a look at this next problem concerning a credit rating system that's supposed to be at least 80% effective or accurate. This one is a hypothesis testing question. It involves a proportion. This one is a one sample problem. And it is also a one-tailed problem because the question is it 80% or is it less than 80%? And because it's a proportion problem, this will involve the test statistic z. So our null hypothesis is going to be that p is equal to the projected value of 0.8, but we have a problem if the value of p is less than 0.8. Okay, so we now get our test statistic z. So this will be the observed value of 0.74 minus the expected value of 0.8 divided by the standard error. And we remember that for the standard error down here, we use the value of p under the null hypothesis if the null hypothesis is correct. So 0.8 as opposed to 0.74 times 1 minus 0.8 divided by the value of n, which is 1,000. And doing the arithmetic, this works out to be negative 4.7434. From this point, there are two ways of proceeding. The first way is to find the value of the critical value. In this case, alpha is equal to 0.05, our default assumption. And so the critical value is negative 1.6449. The second way of proceeding is by finding the p-value, the chance of seeing a test statistic that extreme or more extreme. So that'd be the area to the left of negative 4.7434. And the p-value, the area in blue that got shaded, is actually, using the commands on the calculator or else Excel, 1.05 times 10 to the minus 6. So quite small indeed, about a chance in a million. And so with that, the value of p is less than alpha. Alternatively speaking, the test statistic, negative 4.74 falls in the rejection region, and so our decision will be to reject the null hypothesis. So we'll type that over here. So we reject the null hypothesis. The data suggests that less than 80% of the customers are correctly assessed. For the second part of the problem, we were asked to find the power of the test if the credit rated system is actually 75% effective. So for this, we will use one of the formulas for beta that we found in the textbook and in the lecture notes. And we need to use the formula for beta that corresponds to an alternative hypothesis where I have a less than sign. And so let me just simply write that out. We have 1 minus phi of p naught minus p prime minus z sub alpha times the square root of p naught times 1 minus p naught all over n, and the n is under the square root, divided by, so let me make big parentheses, square root of p prime times 1 minus p prime over n. So substituting in the numbers, we have p naught under the null hypothesis is 0.8, p prime under the assumed alternate is 0.75, minus z alpha, which is 1.6449. So remember, Z alpha is a positive number. Negative 1.6449 is the critical value. Times the square root of 0.8 times 0.2 over 1,000 divided by the square root of 0.75 times 0.25 over 1,000. Okay, so then we just simply plug into the calculator, see what this is, and we get 1 minus phi of 1.152043. Okay, so we need to find the area to the right. So remember, phi is the area to the left of the bell curve. So 1.15 will be about here. 152,043. Phi is the area to the left, so 1 minus phi would be the area to the right. And so using our technology, this works out to be 0.1247. Finally, we need to figure out not beta, but the thing of the quantity of interest in this case is the power. The power is equal to 1 minus beta. And so 1 minus 0.1247 works out to be 0.8753. And so under the assumptions of the problem, the power is equal to 0.8753. In the third part of this question, we are supposed to find how many tests are necessary if we want the power to be not 87.5%, but to be 99.5%. So for this, we will use the formula for projecting a sample size. That formula works out to be for proportions. N is equal to Z alpha times the square root of P naught times 1 minus P naught, going with the null hypothesis, plus Z beta times the square root of P prime times 1 minus P prime, all over the difference between P prime and P naught, whole thing squared. Okay, so in our case, this is equal to 1.6449 times the square root of 0.8 times 0.2 plus Z beta. Okay, so let's pause for that. Z beta, we need to find the power to be 0.995, which means that beta would be equal to 0.05. 0.005. Because the power is 1 minus beta. So we need the 99.5 percentile for the bell curve, and that works out to be 2.5758. So we'll need that number here, 2.5758 times the square root of P prime, which under this particular alternative is 0.75, same as before, 75%, times 0.25, all divided by 0.75 minus 0.8, whole thing squared. And doing the arithmetic, this works out to be 1,257 0.85. And so we'll round up to let n be equal to 1,258. And so we've already done 1,000. If we had a sample size of 1,258, then the power of the test would be 99.5% as opposed to only 87.5% with a sample size of 1,000.